Hello, everyone. My name is Thomas Lin from the University of Toronto, and on behalf of my co-authors and myself, I'm here to present our work, PhysarumSM, P2P Service Discovery and Allocation in Dynamic Edge Networks. So before we begin, here's a brief outline for this presentation. We'll begin by discussing the motivation for this work, followed by a discussion of the requirements and design of the system. Afterwards, we'll dive into the prototype implementation of PhysarumSM itself. We'll then present the preliminary evaluation for the system, followed by a discussion of the use cases to highlight potential applications of this work. Finally, we'll conclude with a summary and highlight future directions. So the motivation behind this work is driven by two main trends. The first trend is the fact that we're observing compute devices getting smaller and smaller, and with their smaller size, they enable mobility. So these apply to things ranging from Intel NUCs and compute sticks to smart devices and vehicles. And furthermore, we believe that these devices may be virtualizable. But we're also observing the same trend apply to wireless access points, such as Wi-Fi hotspots and cellular base stations. And as a mix of these two, the edge network around users will have a very dynamic edge network topology. So the second trend that we're observing is what we call composite cloud applications and services. Now, this is mostly being driven by the microservices and network function virtualization architectures. And we call applications that are based on these architectures composites because they're mostly composed of multiple different intercommunicating smaller services that are likely geographically distributed. And because of this, their overall performance is highly dependent on the placement of these smaller services relative to each other. And in a very dynamic edge, we believe the performance will be always changing. Now, in our past work, which was presented at NOMS 2020, we tried to solve this issue by presenting a client-centric QoS autoscaling system. Now, this system was able to monitor and be aware of the client QoS. And it's able to dynamically autoscale and place microservices closer to the users of those services. And in this way, it was able to improve the performance of composite applications. Now, we asked ourselves, what would happen if the connection to these management plane services are disrupted due to things like natural disasters, network congestion, or other events? For example, recently in Canada, an entire town lost its internet, cellular, and cable TV connections due to a couple beavers just chewing through optical cables. So in this work, we're arguing for the decentralization of service discovery and allocation. We think that because clients themselves are best positioned to detect whenever their client-side QoS to a service degrades, they should be given more autonomy to be able to discover available nearby replicas, or if no replicas exist, they should be able to request allocation of a replica on a nearby compute node. We think that in this way, composite applications and services can react more quickly whenever network conditions degrade. To achieve this, we're going to leverage structured peer-to-peer overlay networks for their fault-tolerant, cooperative, and self-organizing nature, and we think this will enable scalability, high availability, and mobility support for applications. So at a high level, these are the following requirements for this work. The first is that we wanted decentralized service discovery such that clients should be able to discover the existence of replicas. And we note that a service may have multiple different replicas existing in multiple different places. Second, clients should be able to allocate a replica if needed. Third, we want to have some sort of basic monitoring of the infrastructure and the services. So this means being able to collect the CPU memory and network utilization of nodes and services. Lastly, we want some very basic security characteristics in the system. So for example, end-to-end encryption, and we use image hashing, which we'll discuss later, to prevent modified services from being used. Here's the very general high-level architecture of the system, and it's composed of three layers. The first at the bottom is a resource metrics layer, and this is where all the compute infrastructure and network infrastructure exists. And this includes both physical and virtual versions. The second is the information layer, and this is where we aggregate telemetry collected from the resource layer, and also where a component which we call the service registry exists. We'll talk more about the service registry later. Lastly, in the top is our control and management layer, and you'll note one interesting thing, which is that we put clients in this layer. We put clients in this layer because, like I said, we are empowering them in this work to be able to discover services and allocate services as well. And of course, it also includes other traditional cloud management services such as the virtualization daemon. Now, key to this work is our use of hash-based identifiers. For those of you in the audience who know peer-to-peer networks, you'll know that for structured P2P networks, under the hood, it uses a data structure called a distributed hash table, or DHT. And this data structure essentially allows you to take a lookup key and return a list of locations in a network that stores the value associated with the key. And this is essentially what powers popular applications such as BitTorrent or applications such as IPFS. Now, we propose to use a DHT to allow clients to perform automatic service discovery by basically looking up a service key and returning a list of locations where the service exists. To enable this, services in our network are assigned unique service hashes, and these service hashes are computed by hashing the service image itself, which is either a container image or a VM disk image. So the implementation of our system, we designed and built our system using a library framework called libp2p, and we chose this framework for the following reasons. Number one, node addresses are hashes, and using hash-based addressing implicitly enables mobility. Number two, end-to-end encryption is enabled by default between all nodes in the network. Number three, private networking is also a possibility, which enables us to have multi-tenant P2P networks. And lastly, libp2p comes in multiple different language implementations, which enables us to have a polyglot microservices architecture. Specifically in this work for this prototype, we're using version 0.9.2 of libp2p, which was compiled using Go version 1.13. Here's a high-level system diagram of our implementation. The color codes are based off of the high-level architecture shown on the previous slide. Essentially, you can see that any objects with an arrow to the P2P network in the middle are peer-to-peer enabled. We'll go through each of these components slowly. The first and perhaps most important component in the system are the bootstrap nodes. The bootstrap nodes allow new nodes joining the peer-to-peer network for the first time to discover other peers in the network, and they typically exist in some well-known underlay address. Due to their role, they often become some of the most highly connected nodes in the network, and this makes them highly suitable to perform latency monitoring to other nodes. And so we strategically place them in locations such as network gateways where traffic must pass through. And we can expose this latency data, which the bootstraps collect, to Prometheus to centralize all the latency information. And this is shown in the figure here on the right, where all the gateways in regional LANs are running a bootstrap node. And they monitor latency to other bootstrap nodes in other gateways, as well as to nodes within their own LAN. And this is all collected by Prometheus up here. So another major component in our system is the service registry. The service registry is responsible for storing certain metadata regarding components. So this includes a link to fetch or download the service image itself, the compute requirements for running the service, for example, its CPU and memory requirements, and third, its client-centric QoS requirements. And I reiterate, our definition of client-centric QoS means the network QoS that clients need to be able to receive the service. Another important role of the service registry is to act as a lookup service from human readable service names to service hashes. So this plays a role very similar to DNS in traditional TCP/IP architecture. We note that for ease of use, developers can always hard code hashes to prevent the version of service they want to connect to from changing. Lastly, we note that the service registry exists at a well-known service hash, so everyone immediately or automatically knows how to contact it. Lastly, another major component in this system are the LCAs, or lifecycle agents. This essentially is the per compute node virtualization daemon, very similar to a kubelet in Kubernetes or a Nova CPU agent in OpenStack. It's designed to be pluggable, and right now in our current prototype, we use the Docker driver. It's responsible for not only booting up virtualized services, but also for monitoring their resource utilization. And if it notices that a containerized service is idle, it gets reaped, so it deletes it from the node. It's also responsible for caching the service images, and it caches images in order to one, save bandwidth to avoid downloading images every time it's requested, and B, to decrease the time to service. And it enables things such as cold and warm standbys. We define a cold standby as having the image cached, ready to launch the service, and a warm standby as having pre-allocated the actual service, but without activating it yet. And again, like the service registry, it exists in a well-known service hash. Lastly, in order to have backwards compatibility support with TCP/IP services, we developed something called a service proxy. So this service proxy, essentially, it opens up local TCP/IP listening sockets in the container or in the local host and allows a service to connect to peer-to-peer services by talking through the local sockets. What local sockets are opened are configurable at runtime. So you can dynamically ask the service proxy to open a new connection to a new peer-to-peer service, and it'll open a local socket as a proxy. So whenever you want to contact a P2P based service, it does QoS based replica selection. So again, a service may be composed of multiple different replicas. So here on the right, we see a service A that's advertising itself based on its service hash. A client comes in and all it says is it wants to connect to service A. And so its P2P proxy does a lookup to the service registry and it sees that the name service A maps to a specific service hash and it uses this hash to search for an instance. It then connects to the instance and measures the initial round-trip latency. And if it's less than the maximum latency as specified in the QoS requirements in the service registry, then it's okay to continue with the connection. However, if it doesn't meet the latency, as in this case, we'll see here, it tries to connect, it sees that the end-to-end latency to the service is over the maximum latency as specified in the service registry. Then what it does is it tries to find a LCA agent that meets the latency and requests that a new service A replica get booted up in that compute node. An interesting feature that we wanted our system to support from the beginning was the easily composed peer-to-peer based NFV service chains. As you can see in this example, the service registry has 3 VNFs, 1, 2, and 3, each with their own maximum latency QoS requirements. Each VNF is essentially the client of the next VNF in the chain. In this way, each VNF, or the original client, is responsible for ensuring that the next VNF in the chain meets the QoS requirements relative to itself. Here you can see a flowchart of the high-level logic when a peer-to-peer client or service connects to another service for the first time. I'll skip over the details as you can look it up in the paper or pause the video to look at the flowchart in detail. What I want to talk about is what happens after two nodes establish a connection with each other. They continuously monitor the quality of the connection to ensure it meets the QoS requirements. But, however, we found out early on that if we just had a hard requirement, it would sometimes lead to hysteresis, where, for example, in this case, the latency, it goes over the hard requirements and then it disconnects and then it returns back to being okay and it reconnects to each other. This kind of behavior is undesirable, and to solve this, we created two types of requirements in the service registry, a hard QoS requirement and a soft QoS requirement. If the metric is above the soft requirement but below the hard requirement, it's labeled as undesirable and the nodes continuously monitor for some time. If after some time it's still unreliable, then it disconnects. However, if it crosses the hard threshold into being unusable, it disconnects immediately. And now we'll talk about some of the evaluations we performed on our system. Our first evaluation focuses on measuring the P2P search and allocation time. In this scenario, we use a simple HTTP-based server connected through the P2P proxy we previously presented. No replica of the server currently exists, and so when you try and query the server, one needs to be dynamically allocated. We use a cold standby scenario, meaning that every compute node has the image already cached. On the right here, we see the CDF of the timing for when a client issues a request It searches the DHT network, figures out that no replica exists, allocates one, and then receives a response. The median time of the total sequence is about 2.17 seconds. Out of this 2.17 seconds, we note that the allocation stage itself takes up roughly 70% of that time, with a median time of 1.58 seconds, just dedicated to the container allocation itself. So next, we want to showcase a data pipeline application of an NFV service chain. In this service chain, we have a set of roadside sensors that periodically collect some sort of data, for example, the temperature or the speed of traffic, etc. Now, because these sensors are short range, their goal is to transmit their data as soon as possible to some sort of aggregator service. Luckily, we have a set of compute nodes on buses that periodically come by and pass the sensors. When they pass the sensors can trigger an allocation of an aggregator service on them to upload their data to. So in our scenario, the interbus time is roughly 55 seconds, and the aggregator's client-centric QoS is roughly 5 milliseconds for the soft latency limit and 10 milliseconds for the hard latency limits. After performing some sort of pre-processing on the data, the aggregators then upload the analyzed data to the remote cloud for long-term storage and analytics. Now on the right-hand side here, we see from the point of view of one of the sensors, its latency to the aggregator it's currently connected to. So when the scenario starts at time equals 0, it's connected to an aggregator on a bus that's driving away. Now at roughly t equals 20 seconds, the soft latency is exceeded, and so the sensor starts seeking out another bus to allocate an aggregator on. At roughly t equals 36 seconds, it allocates a new aggregator on a bus that's just passing it and switches its connection. Now, immediately, it drops the latency, but unfortunately, because that bus is just passing it, it starts to drive away, thus increasing the latency once again. As it starts exceeding its soft latency limit again, the sensors then begins to search for another bus to trigger an allocation of a new aggregator. It eventually does so at around t equals 70 seconds and switches its connection to the bus. Luckily, this bus is now approaching, and so its latency starts decreasing. And as we can see here, as it reaches about t equals 95 seconds, which is when the new bus begins passing it again, and as it starts leaving the sensor, it increases the end-to-end latency again. And so this pattern repeats over time as buses come and leave. In order to gauge the suitability of our system for small edge devices, we collected the component resource utilization based on the data pipeline application that we had just presented. Of course, these numbers will be very different depending on the type of application you're running and the logic of the application itself. But as you can see here, in terms of the memory and CPU utilization, we believe that these numbers prove that it's quite suitable for smaller edge devices. I'll leave the reader or the viewer to pause or look into the paper for details about these numbers. So now we want to quickly cover some potential use cases, just to drive your imagination. So we imagine that our system will be particularly useful for building applications and services to survive areas such as, for example, disaster zones that have very limited connectivity to central clouds, to be particularly useful for applications on large passenger vehicles such as buses, planes, trains, cruise ships, Navy ships. So for example, if the ship on the right loses its satellite connectivity, the applications that users are running on board should be able to somehow survive. For example, military field operations when you're out in the wild. For pop-up festivals where people congregate in the wild without traditional communication systems. On the right here, you have an example of Burning Man. Or for any sort of self-healing management plane that has to automatically reconfigure itself depending on the conditions of the connectivity in the network. And we note that the concept of self-healing management systems has been a classic and reoccurring theme throughout science fiction, ranging anywhere from Terminator to the spaceship and passengers, where damaged parts of the system can be compensated for by actively redeploying the management functionality elsewhere. So to quickly summarize our presentation, our work is premised on our vision of a future compute-rich landscape that's full of mobile devices and access points, which will result in a very highly dynamic edge network topology, impacting the performance of composite applications and services. We think that because the clients themselves in this dynamic edge are best positioned to detect whenever the network quality goes down or the service they're connected to suffers some sort of impairments, they should be given the ability to automatically discover other service replicas or request new ones. And so to realize this, we present PhysarumSM, our prototype of a service mesh based on P2P principles that allows clients to independently discover replicas meeting certain QoS requirements, or allocates new replicas on candidate compute nodes. The system uses hash-based service identifiers for versioning, and it uses hash-based node addresses to enable mobility. We presented a P2P-based service proxy for backwards compatibility with traditional TCP IP, and also we're able to support peer-to-peer based service chaining. In terms of future work, we're looking on a few avenues. First, we're looking at, for example, peer-to-peer transfer of images, which will save bandwidth of nodes. We're looking at potentially enabling multicast or pub/sub applications. We want to look more into how to control access to nodes to prevent unauthorized clients from requesting allocation, and this will also further enable us to support multi-tenancy. We want to investigate more on allocation policies and algorithms to consider, for example, a node's connection history. And also we want to investigate more into other service reaping policies and algorithms. And with that, thank you guys for listening. Are there any questions? I'd be happy to take them.